Hello, everyone. Welcome to seminar. Thank you all for being here. Today we have Bernard Coakley. He's our visiting scholar from University of Alaska Fairbanks. Bernard Coakley was born in Detroit, Michigan, and attended two of that state's finer universities, eventually earning a degree in geology from the University of Michigan. He attended Louisiana State, where he earned an MS degree, and continued on to Columbia University, where he received a master's in philosophy and a PhD. He had a postdoc at the University of Wisconsin-Madison and returned to Lamont Doherty as a sophomore research scientist. During this time, he began to work in the Arctic Ocean, which has become his almost exclusive obsession since 1993. It's a year after I was born. After 5 years on soft money, he went to Tulane University as an assistant professor. For the last 21 years, he has been at the University of Alaska Fairbanks. To better understand the Arctic Ocean, he has sailed on U.S. Navy fast attack submarine Sex 1993, 1995, 1999. On icebreakers.
Dale was on a couple of those. Dale. The bearded fellow there.
On icebreakers, United States Coast Guard cutter Healy, the RV Sikuliaq, and Polar Stern. Not the Polar Star, Polar Stern. So look it up.
Well, it is Polar Star, but it's in German.
But there's a German, sorry, no, we're anyways, and on relatively unreinforced vessels, RV Langseth, such as the RV Langseth. He has been to the North Pole 6 times, though he wonders why this geographic singularity excites anyone. Ladies and gentlemen. Ready.
That's when I started. Ladies and gentlemen, boys and girls, children of all ages. I'm here to tell you about the Arctic Ocean because that's what I do. You know, I go out and tell people about the Arctic Ocean. I try to cage various trips to the Arctic Ocean by appealing to funding agencies, better angels. That works sometimes. But the thing I really like, the theme in this talk, if there is one single theme, is that the Arctic is a weird place. The things that we know from working in the ocean, global ocean, don't apply in obvious ways. So one of the main themes of my research program has been trying to learn enough that we can make it more like a normal ocean. Now, one aspect why this is important is that in the Arctic, we do it backwards. Every other place on the globe, we've understood the oceans, and then the continents make more sense. In the Arctic, we don't understand the ocean yet. So the continents are, you know, we don't have that kind of constraint on interpretation of continental geology. And this puts us at a strong disadvantage. Whoops, wrong way. Yeah, backwards. You see. The talk itself will emulate. So I'm going to give you a brief explanation of plate tectonics, because I know there are engineers in the room. And for you, I'll talk slowly and use short words. But this provides some important background, even for the people who know this stuff. It sort of frames what I have to say about what we do and don't know about the Arctic. Mapping the Arctic, there's a history of mapping in the Arctic. In 1993, when I went out on a US Navy submarine, the Pargo, no, it wasn't Pargo. No, it was Pogi was 96. It was Pargo. Anyway, our hypotheses when we sailed was about the location of the features. And it turned out that we were wildly misguided by hundreds of kilometers and thousands of meters in elevation. Why this cruise? Good question. NSF asked me that too. And what did we see? So, you know, one way I like to describe plate tectonics, and these are the rigid plates that cover the Earth's surface, is that with plate tectonics, geology went from being an empirical science, describing stuff, to being a predictive science. Because now if you knew a few things, you could say, well, this is where the earthquakes will be. This is where the copper ore is. This is where the volcanoes are, you know, and so on and so forth. And so, you know, the idea that the Earth is covered by a series of relatively rigid plates that are in constant motion really has expanded our understanding. Oops, I just keep going backwards. And one of the very important aspects of this is a magnetic anomaly profile. It was collected from Miltanen 19 by a guy named Walter Pittman, who passed away recently. But What to say about Walter? Anyway, the incredible thing about this magnetic profile is if you flip it over on itself, it looks pretty much the same. So this data set was taken as proof that seafloor spreading was a real thing. And now the amazing thing that lets you do, these are all reversals, right? So the poles in the north, the poles in the south, poles in the north, poles in the south. So the magnetic minerals are aligned in different directions. But these events, these reversals, are a global event. So the boundaries of these segments of oceanic crust have age significance. And you can map the whole ocean. Wow. The age of every place in the ocean is known. The age at which that piece of crust formed. That's kind of amazing, isn't it? In the Arctic, we don't have that, except for over on the side where we have this ultra-slow spreading ridge called the Gackle Ridge that I'll get back to. So, this is the way that we can understand the oceans. Now, some stunning facts. When I teach intro geology, I like to start every lecture with a fact that should just knock you out if you're awake. And, the continents are old. All of them. I mean, they stand differently because they're composed of different material, just based on isostasy. The oceans are young. The oceans are young everywhere. And one of the basic insights that led to plate tectonics was the recognition that continents and oceans are uniquely different things. Now, one of the things that's interesting about the Arctic is that we appear, in one part of the Arctic, to have something we can call oceanic and something we can call continental, but there's a fairly broad band of material between what we can call oceanic and what we can call continental. And characterizing that material is necessary to understand it. So every point on the Earth's surface is in motion, which is easy enough to say, but think about it for a minute. We like in our mind to imagine something is fixed or something isn't moving, but everything's moving. That should trouble you maybe. And we understand the history of the continents once we understand the history of the oceans. So this is the International Bathymetric Chart of the Arctic Ocean, fabled historian song, the output of years of effort by Martin Jacobson and his many minions. And the thing that we know, or a number of things we know, is that the Eurasia Basin, formed by propagation of the Mid-Atlantic Ridge up across the Arctic, and it trimmed off the edge of the Barents Shelf. And that formed in the Cenozoic, so it's formed in the last, say, 58 million years. The other part we call the Amerasia Basin, and so far as we know, that formed in the Mesozoic, the age of the dinosaurs, and has been tectonically inactive ever since. Now, the other features in the basin are Lomonosov Ridge, and this is this long, narrow sliver of continental material that was shaved off the edge of Eurasia by the propagation of the Mid-Atlantic Ridge to the north. You can think about it as being like Baja California after 60 million years. The Gulf of California, there's a spreading center that's propagating up, and Baja is separating from the continent. And similarly, Lomonosov Ridge did that act, but some time ago. And the reason it did that is because continents are weak. So plate boundaries prefer continents, just for the record. And then, whoops, other way. Hello. Lomonosov. There's the Chukchi borderland. We're going to talk about that a lot. And as I mentioned, continents and oceans are different things. And the elevation of the Chukchi borderland is enough to tell you it's continental, just by itself. Mendeleev Ridge, Alpha Ridge, people tend to run these together. Alpha Mendeleev Ridge, and the currently accepted explanation for the Alpha Mendeleev Ridge is it's a large igneous province, an effusion of basaltic magma onto the seafloor. But the Alpha Mendeleev Ridge has been honored with every possible hypothesis as to its origin that exists for any feature on the seafloor. So the structure of the basin is basically banded. You've got the Cenozoic Eurasia Basin, the Mesozoic Amerasia Basin, Lomonosov Ridge, Alpha Mendeleev Ridge, Chukchi borderland, and then the Gackle Ridge, the ultra-slow spreading ridge that separated these, and then, oops, Canada Basin way up in the corner there. So just to give you an idea of what it was back in 1993, this was the map we had of the Lomonosov Ridge in 1993. It looks like a contoured hot dog. And this is the profile, the bathymetry we expected. So I was on the Argo, and I went to the quartermaster and I said, well, we shouldn't see this for another 100 kilometers or so. And he said, well, bottom's coming up now. And so, you know, we encountered it, I don't know, 125 or so kilometers is a different location, and the elevation more than 1,000 meters higher. And this is true everywhere in the basin. Everything we did not know. We also have the Arctic Gravity Project grid, which I've been involved in. So we've compiled a lot of gravity data. So this gives us an image of the gravity anomalous gravity field of the Arctic. And you can think about the anomalous gravity field in a very simple way. It's that there's more stuff there. So over the Hawaiian Islands, you've got a big gravity high because you've got this stack of basalt on the seafloor, okay? But there are other features in it that you can interpret in terms of crustal thickness. So we've got bathymetry, we've got gravity, we've also got magnetics. So we've got the triad, the basic set of observations that we use in the oceans. Now, one of the things that's different about the Arctic is, you know, if you get a cruise, you go off to Tahiti or something, you'll be pretty sure you're going to be able to do everything you want to do. When I put in a proposal to NSF, I have a science plan, but I have to kind of close my eyes and say, yeah, that's what we're going to do, because it's tentative until you get there. Now, one thing that's been working somewhat to my advantage is this is a picture taken from the webcam up on top of Healy in the year 2007. Continuous ice, ponds on top of it, probably rotten. And this is from Larry's cruise in 2012, about the same place, complete open water. And this has been happening year upon year upon year. The sea ice has been retreating. 2012 is still the record for the largest retreat. So just to give you an idea, when I was planning my cruise, I went to the National Snow and Ice Data Center, and I downloaded grids of ice data. And each of these lines is the position of the ice edge on 15 September. That's the date typically you hit the ice minimum. So it's the maximum retreat. So these yellow lines, you know, like this is 2016, this is 2019 there, 2017, 2016 again. So that's where the 15% concentration of ice is the ice minimum. So that's where you hit the ice edge. The red dashed line is the average position of the ice edge from 2008, 2019. So what you can see is that the ice minimum, the Chukchi borderland is open water. Most years. This is what it was in 2021 when we went up. So this is the ice edge here. And here's the ice edge too. So there's a band of ice. And this is, some of this is multi-year ice that was swept off the Canadian Arctic Islands, which is one of the few places there's multi-year ice in the Arctic anymore. Mostly it's annual ice. And this was an obstacle. And I think it suppressed the retreat of the ice further north. So it was much more difficult for us to operate. And that made a huge difference for how the cruise was conducted. Now, this story, you've probably seen this in the news, sea ice continues to retreat, even in 2021. But it doesn't tell you where. So it's retreating somewhere. It didn't retreat where I wanted to go. And this complicated all kinds of data acquisition. This is collecting multi-beam data from Coast Guard Icebreaker Healy. You back and ram, back and ram, back and ram. And when you go to ram, you accelerate fast enough that the transducers are uncovered, and you get these little splotches of data. That's how ice affects data. Now, the Amerasia Basin, bathymetry, gravity, and magnetics. Now, what we see here is this is the Canada Basin. It's a relatively deep, nearly oceanic basin. There's the Chukchi borderland again. Canada Basin, Chukchi borderland, and the magnetic signature for the Canada Basin. Now, if you squint a little bit, and I'll give you some help on this in a minute, you can see there's kind of a gravity low right here. And you can see, again, this requires a little more squinting, that there's paired magnetic anomalies as well. Oops. Now, the way we understand the Canada Basin right now is based on a paper that was written by a guy named Jere in 1956, the year I was born. Just looking at me, that should tell you something. And Jere described this as a stenochasm, a word that has gratefully gone out of use. And basically what he thought is that it opened like a pair of scissors. Okay? So Alaska and Siberia separated from the Canadian Arctic archipelago around a pivot in the Mackenzie Delta. And this is still the standard theory for the opening of the Canada Basin. So what most people do is they say, okay, it opened like this. And then the problem is, well, this wasn't very well known in Kerry's time, the Chukchi borderland. But now it is. It's this big chunk of continental crust. Continental crust is, by geologic standards, indestructible. So you can't make it disappear. So if you want to bring these two sides back together, you've got to find out where to hide the Chukchi borderland. So tectonic models that exist for the basin distinguish themselves largely on what magic they want the Chukchi borderland to do. Some people will slice it up and spread it out. Other people will have it rotate back into the Siberian shelf. No evidence for those, but that's what they have to do. And so part of the reason that Kerry's model is still considered reasonable is that we don't have the data to refute it. He got there first. He said, this is what it is. And nobody can disprove it. He's dead, but never mind. He probably doesn't care. But anyway, so the windshield wiper or the pair of scissors dates from Kerry. So what I've tried to do is to, instead of thinking about, okay, I've got this global or this overall tectonic flow, and I need to figure out how the pieces fit in. I've said, well, I'm going to look at the pieces and figure out how they relate to each other, and then try and reconstruct the tectonic history from those pieces. So study the individual features, and this is enabled by these maps of gravity and bathymetry that I've shown you. Hello. So the science objective of the cruise was very modest, the origin of the Canada Basin. Oh. So we wanted to look at the crustal structure of the northern Chukchi borderland, because I'd done the southern from R.V. Langseth in 2011. We wanted to look at this extinct mid-ocean ridge that may exist at the bottom of the Canada Basin. And we wanted to look at the adjacent extended continental crust. Okay? So the relations between these features are something that should be able to tell us something about how the basin formed. Now, there are a couple of questions. One is that, okay, maybe we found this one segment of oceanic ridge underneath the Canada Basin. But plate boundaries don't exist in isolation. They connect like the seams of a baseball. So where does that ridge connect up? So we collected all this data. You know, most geophysical cruises are noisemakers. You know, you collect data at various frequencies. You see different things because of the frequencies of the data. We had multichannel-seismic from the Geologic Survey of Denmark and Greenland, their portable MCS system. We had an EM302 and a Topaz PS18. These are the air guns. They were operated by 3 very capable engineers from the Geologic Survey of Denmark and Greenland, Per Trinhammer, Lars Rasmussen, and Thomas Funk, who is German, but he's at yes. They're very clever about how they designed this thing. So there's the streamer, there's the umbilical for the guns, and it's just on one container. This is what these things look like when they're going off. So each of those buoys is attached to an air gun. There's a shot. So each one of these shots goes off, right? You release 2,000 psi air into the water, and it goes bubble pulse. And then you record the returns from the low frequency energy that you put into the water through those air guns. And what you can do if you're clever, and we're clever, is you can reconstruct an image of every change in velocity of the stratified material below the seafloor. This is the standard technique of oil exploration. Now, we're not exploring for oil. And don't ever tell anyone we are, because half of northern Alaska thinks we're doing that anyway. But this is the standard technique of oil exploration, and if it's working right, we can image the stratigraphy down 5 or even 10 kilometers. Now, here's the sad story of the cruise summarized. The green lines are the lines I hope to sail. The red lines are the lines we were able to sail. And you can see that these lines are kind of trembly, like they were written by somebody with a weak hand. That's us trying to, icebreaker is kind of a misnomer. Mostly they're ice avoiders, because the captains, they don't like to scratch the paint, and they don't want to burn too much fuel. So, and Sikuliaq is a pretty good vessel, and it's a great vessel for working in the marginal ice zone. But we were encountering thicker, more continuous ice than we expected. So some places we were just locked out based on the ice. So we did 3 basic surveys. One, I wanted to collect crossing lines on lines I collected in 2011. And this would help us be able to drill these sediments as part of the ocean drilling project. The other, I wanted to extend the survey I'd done down here up into the northern Chukchi. Then we wanted to do ocean bottom seismometer surveys, one on an area that's been identified as oceanic crust, one on an area that's been identified as transitional crust. And we got through that, we had time to kill, so then we did a survey that straddled this extinct mid-ocean ridge that we think exists. This gives you an idea. All these lines are all the multi-channel seismic data. The blue lines were collected as part of the ECS program in a joint US-Canadian project. The red lines are the data I collected in 2011. You see how straight those lines are? That was open water, all of it. See how crooked these lines are? That wasn't open water. Should have been. And then the purple is polar stern lines. The green is a line Yngve Kristofferson, John Hopper, and I collected in 2005 from Healy. Now, just to give you an idea of part of the complexity of Alaska Arctic geology, is this is a seismic refraction profile we collected in 2005 over the Mendeleev Ridge. And you can see that the stratigraphy is complex. There are unconformities, erosional surfaces potentially. There are places where layers pinch out. That can be depositional, it can be erosional. But we have no clue of the age of any of this. When part of the irony of doing a drilling proposal, which we've done for the Chukchi, based on the data I collected in 2011, is you have to give them an age model. Basically, you have to tell them what you're going to find. And okay, we know the surface is now-ish, but as soon as you go into the stratigraphy, as soon as you go through an unconformity, Don't know. So these are these cross lines. The red lines are the lines I collected with Langseth. The blue dots are sites we proposed for ocean drilling. These red and blue lines are cross lines, because the great fear of the ocean drilling program is that, they're the opposite of an oil exploration program. If they drill into pressure, I don't know, an oil reservoir, a gas reservoir, they have no way to control it. It's going to come back up at them. So what they want is they always want crossing lines, and they want to be able to rule out a four-way closure, that you'd be drilling into a high that might trap pressurized fluids. Okay, so that's why you need the cross lines. So we collected these data. Again, you can see how we're kind of wandering around. It looks a little bit like a drunkard's walk. And if you're drunk on ice, I guess that could be the case. Here's, I'm going to show you this line here from the Langseth data. And I'm going to show you these two sites, which we proposed for drilling. Oops, wrong way. Here. That's the stratigraphy on top of the Northwind Ridge and the Chukchi borderland. Unconformities, changes in reflection character, indicating a change in sediment caliber and character. It's a very complicated stratigraphy. But as soon as you get one below one of these unconformities, you could be in the Paleozoic. You could be in the Precambrian. We don't know. And this isn't a positive aspect from the point of view of the drill program. They want to know what you're going to find. I'd like to know too, but until I drill, I can't tell you. Now, this is another line we collected from Langseth, and on the index map there, it's B to B prime. And this is these interior grabens in the basin. Okay, what you can see is that in some places, the stratigraphy thickens into what is a border fold. That'd be called the Sin Rift sequence, the sequence that was deposited as this thing was kind of pulling apart. Okay, have any of you ever seen the red bed sediments on the west approach to the George Washington Bridge? Those are Sin Rift sediments. And they were deposited when the Newark Basin was opened. But the Sin Rift sediments are very restricted. We don't see them everywhere. And the only way to explain that is if much of the Chukchi borderland was below sea level, so that the material didn't rise above sea level, didn't generate sediments, didn't get eroded. Now, these other sediments, the green and the yellow here, these are all sediments that are coming off the Chukchi Shelf between northern Alaska and Siberia. And they formed this huge progradational delta that goes right down the throats of these extended rifts. The purple reflections are coming off the shelf and are sediments that were mobilized by glacial contact on the seafloor. So in parts of the seafloor north of Alaska, there were real continental glaciers. They were eroding, they were scraping, and they deposited these sediments in the basins. Now, this is our Chukchi borderland survey. Again, the sad story of the green lines I wanted to sail and the blue lines I got to sail. Somehow we managed to collect a lot of seismic reflection along these lines. And then you'll see up here, we're collecting seismic reflection, then we don't. And that was when Lars and Per had to go to sleep because they'd been working just too hard and it was going to get dangerous. And so we shut down the MCS for a while. They got some rest. But again, you can see, comparing what we wanted to do to what we did and how difficult it was to do it, it's kind of sad. Now, this is one of the lines. The line is indicated in red there that we collected. And again, you see these rift basins, but if you notice, the sediments in the rift basins are much thinner. And that's because this big progradational sequence coming from the shelf pinches out. So you have a much lower sedimentation rate in the basins in the north. You can see too that the stratigraphy up on the ridge high is relatively complicated. Now this is here to highlight what a great success my grad student has had in processing this data. You see these repeated packages of reflections? Those are multiples. And what happens is, it bounces off the sediment once, it bounces off the water, bounces off the sediment again, bounces off the water. And when you have a real stack of multiples like you have here, it means the bottom is really hard. So it's reflecting multiple times. And each one of the multiples is an image of the stratigraphy below the seafloor. By using a processing package called Vista, my students have been able to suppress a lot of the multiples. And in some places, the multiples can really complicate the interpretation of the stratigraphy because they overprint it. Now, as a part of the Extended Continental Shelf program, the Canadians threw a lot of what are called sonobuoys. And these are just floats with a radio, and they drop a hydrophone. As you sail away, the sonobuoy will record the returns from the shot and transmit them to the ship. And what you can do is, if you get enough offset, you go past something called the critical angle. You go from reflected energy to refracted energy. It's a way to see deeper into the crust. And based on how they interpreted their sonobuoy data, they found all these white squares were oceanic material. The green squares were transitional, somewhere between oceanic and continental. And the black squares are continental. This came as news. So what we did to try and test that, the disadvantage with sonobuoys is you just sail away, right? So you get a one-sided profile. So you can tell the depth of various refracting layers. You can't tell anything about the orientation. So with ocean bottom seismometers, you can see more. And this is a stronger test of their hypothesis that part of it's oceanic, part of it's continental or transitional continental. So we set up the OBSs on what we believe is transitional continental and what we believe is oceanic. Now, this brings up a sad story too. Again, you can see how convoluted the lines are. You're supposed to sail the green lines, not the red ones. And we had 12 OBSs on board. We wanted to deploy 11 in 2 crossing lines. We could only put out 4 in one place because that's all the ice would let us do. We could only put out 2 in the other place because that's all the ice would let us do. And recovering them is a little tricky. So here's an OBS, and it's on this cross of iron as opposed to the cross of gold. That's another story. And you see, this is the release, right? So you set them out, you leave them out, they run, they collect the data, and then you come back to them and you hit them with an acoustic signal. And when you hit them with that acoustic signal, a wire here is supposed to burn, opening the clamp, releasing them so they float up. The problem is it takes about an hour when you're in deep water. And the ice is shifting around. And you don't want them to rise up under the ice. So it's sort of you're shooting. And it's very exciting because they cost about $14,000 each, and losing them, you're on the hook to replace them. And this is the kind of record that you get. And this is provided by Thomas Funk, who was one of the engineers who was on board. So he spotted a MOHO reflection, a 5.8 kilometer per second layer, a crustal refraction at a higher velocity, and then a mantle refraction. So what we've done is we've imaged down into the mantle. And this is a hyperbola, right? Because as you sail away, it's not the linear distance from the OBS, it's the hypotenuse. So the hyperbola is the travel time record of that hypotenuse difference. Okay? So, you know, we're getting somewhere with the refractions and reflections, so hopefully we'll be able to see deeply into the crust and make a statement about what that material is. So here's the gravity anomaly for the Canada Basin, Chukchi borderland. So there's northern Alaska, here's northern Canada. And you see this trough here. Well, lo and behold, that's a mid-ocean ridge, we think. Okay. And if you look in the seismic reflection that was collected as part of the Extended Continental Shelf Project, you can see a low, a trough associated with this gravity anomaly, which makes sense. It's full of sediment. That means it's a gravity low relative to the adjacent areas. Now, what you can do, should you wish, is you can stack the anomalies, try to bring out the signal. If you look at the magnetics, there's a weak pairing of magnetic anomalies on opposite sides of that trough. And so I tried stacking them with the idea that, okay, if I have a bunch of iterations of it, maybe I can see it better. And, you know, again, if you squint, maybe you can believe it. Maybe not, but it shows up very well in the gravity. Oops, wrong way. So what can we do with this? Great, it's a mid-ocean ridge. We can start with that. That's a hypothesis we can work with. Well, what kind of mid-ocean ridge is it? Well, as it turns out, a really good analog for it might be the Gacko Ridge, which is that ridge I talked about earlier that propagated up from the Atlantic and slivered off Lomonosov Ridge from the Barents Shelf. Now, why would you say that? And here you can see the Gacko Ridge in bathymetry, you can see it in gravity, and you can see it in magnetics. It's closer to the surface, and it was formed in the Cenozoic, so the magnetic anomalies are much clearer than they are on that ridge that may be at the bottom of the Canada Basin. Well, the Gacko Ridge is the slowest spreading ridge in the world ocean. Okay? The full spreading rate, where it disappears under the shelf in Siberia, 0.5 centimeter per year. If you get back over towards the Greenland, Svalbard side, 1.25 centimeters per year. Dredging on this ridge has recovered altered peridotite and gabbro, not volcanic basalt. I mean, in some places they get basalt. But the thing is that this thing is spreading so slowly that it's not producing that much basalt. Either the basalt is being frozen out before it gets to the surface, or if the cooling goes deep enough because it's spreading so slowly, you could even suppress the formation of melt. So an ultra-slow spreading ridge is a unique thing in the ocean. Now, what are the other things that we know about Gacko Ridge? Well, the ridge axis opens the polar opening. You can describe the motion between any two plates as a rotation around a pole. And in the case of North America and Europe, the pole for the Atlantic Ocean, for the separation of those two, is in Siberia, just off the Siberian shelf on land. So it's approaching the pole of opening. And if you remember the geometry of these things, the motion between the two plates goes to 0 at the pole. So an ultra-slow spreading ridge is close to its pole of opening. Okay? It's a sinuous ridge axis without obvious transform faults. That's weird. I mean, look at it. It's like a snake, and if you track it back to the Lomonosov, the Barents side, you can see that the geometry of the ridge is still what it inherited from the original opening. The axis disappears under the Laptev Shelf slope. And the Gacko Ridge, probably, based on GPS work that a guy named Misha Kogan has done in Siberia, probably connects up with the subduction zone in the Pacific. In the south, it connects up with the Atlantic, not a problem. And it continues south through the Gacor, through the Atlantic Ridge. Whoops, wrong way again. So what we did, we had some time to kill. We collected these crossing lines and these lines parallel to the axis. And I just laid out the track and we went as far as we could in the time we had, because I wasn't going to get home early, whatever happened. Now this gives you an idea of what this looks like. Okay, so here's this line, yellow. And you can see that the basement is fairly smooth. There's no evidence of offsets or steps in the basement, which you'd expect to see if there were fracture zones involved. In fact, a paper came out that was done by Arne Dossing and Ruth Jackson. And they hammered on some gravity data until they convinced themselves they saw offsets in the ridge. I don't think they're real, because this basement is smooth. So this is permissive of interpreting that extinct ridge as an ultra-slow spreading ridge. So what does that get us? Well, it's a feature, not a bug. It's sinuous, just like that gravity anomaly I showed you. You know, the connection to the south, at the time when the Canada Basin was forming, there was active subduction in the formation of a mountain range called the Brooks Range in northern Alaska. So that's not a problem. Where does it go the other place, the other side? I don't know. But that, you know, if we could know that, because, you know, plate boundaries don't just stop in the middle of nothing. They connect. Where is that connection? And I'd hope by, you know, some of the lines that I had that were going up to the northeast to actually take a look for that. Thank you, ICE. And then the other question is the direction of propagation. So we're just getting started. My student, Visnu Priyantu, who's from Indonesia, and it might be the first Indonesian to have made it to 80 degrees north. He might be, I don't know. And this will be his PhD thesis. And we've been working out how to process the MCS data. The problem with this is, on Langseth, we had a 5 3/4 kilometer long streamer. And that gives you so many options for imaging the sediment. On Sikuliaq, we had a 200-meter streamer, 32 channels, and 3 of the channels were defective, so we had to kick them out. This really kind of puts us in a box in terms of what we could do for processing. We had a number of COVID challenges. In a way, it's a miracle we even sailed. We had to get visas for 2 Danish cruise participants. Thomas had a government visa, a government passport, so he could travel, but the 2 Danes couldn't. We had to deal with sea freight. At the height of the COVID, sea freight kerfuffle. And we had to just get sufficient staff for the cruise. My wife came. My 2 kids came. I told them I was going to work them by like rented mules. They didn't believe me. Ha! And we had a 1-week pre-cruise quarantine in Anchorage. It takes a village to have a science cruise. It really does, and this one more than others. Now the good news is that we were able to sail, which I still regard as something of a miracle, because at one point, you know, we're talking about 6 containers from Aarhus in Denmark to Seward in Alaska. And when we first started looking around, yeah, okay, 7,000 a container, and they'd guarantee a shipping or a delivery date. When we actually went to book it, they say, well, it's 18,000 a container, and you'll get it when you get it. That doesn't work with ships. So Frank Rack, who some of you may know, he's the Arctic logistics guy at NSF. Frank was an absolute hero, and he footed the bill for air freight, military airlift, flew those containers from Aarhus to Elmendorf outside of Anchorage. And oddly, if this had happened a week later, we used 2 C-17s. If it happened a week later, those C-17s would have been in Kabul.
Oh,
because of the evacuation. We could have gotten the sea freight containers to Kabul. What we would have done then, I don't know. Brian Van Pay, who's some of you know because he's involved with the ECS effort from the US State Department, went to bat with the embassy in Copenhagen, and we were able to get what's called a national interest exemption for our Danish friends so they could come and work like dogs. The crew of the Sikuliaq, the science party, and an old friend, John Hopper, who did not give up. Now, the good news is that we got away from the dock. The bad news is the ice sucked, so be careful what you wish for. Oops, I think that's it. That's it. That's the end of my story. I guess, questions?
Again,
No, go ahead.
okay, it's kind of an off-topic question, but I'm curious about when you went up in a military submarine, how did you get access to a military submarine and what kind
Well,
of data?
Dale and I showed up at the Pentagon one day, and we challenged a guy to arm wrestle us, and if we won, we got the sub.
Yeah.
No, that was arranged partly through a guy named George Newton, who some of you may have met. George was the chair of the Arctic Research Commission at that time, a retired submarine captain. And because of various kinds of business things, the Navy agreed to, the first cruise in '93 was called a blind date, where we just see if we can work together and not kill each other, and that happened. No one got hurt. And then they committed to 5 more cruises, 95, 96, 97, 98, 99. I sailed again in 95. What years did you sail, Dale?
98, 99,
Yeah, and then we,
and the shakedowns for 95, 96, 97.
partly through the offices of a guy named Marcus Langseth, who's the one they named the Vermont research vessel after.
So,
We were able to get NSF to fund a swath mapping system
okay.
and a sub-bottom profiler for the last 2 years. Dale was the lead engineer on that. And it mostly worked.
Nice.
Almost entirely, actually.
It was a vast improvement on the available data.
Yeah, well, that much is true. So the Navy, for a variety of reasons I've heard speculation about, but I don't know, agreed to do this. And it was great because it provided us with access to the Arctic Ocean when we didn't have icebreakers. We didn't, they had the Polar Sea, the Polar Star, but they're both half broke half the time. One is all broke. What's that? Yeah.
They're chronically broken.
Yeah.
Hey, Bernie, David here, Dave Mosier.
Who's the voice of God?
How you doing?
David,
Just a quick
Hey,
question.
Mosier, you again.
Oh my
Me again.
goodness.
A quick question about the line you showed that you said was smooth basement. In that area that we mapped Deping and others mapped as oceanic, he formed a little box around that, and that has rough basement. Outside of that area, basement is smooth, as you showed. So I'm not sure where your line was relative to that white box that Deping drew in the middle of the basement or the basin. But you got to account for the opening of Canada Basin somehow, and as you know, it's really difficult to account for that degree of opening with that rotation model. Sure. And there's a huge amount of transitional crust, we believe, from those velocity analysis, so which may result in your smooth basement. I guess the question is, where's that line relative to where we know we have oceanic basement?
I think it's within that band of material that we have oceanic placement.
Okay.
I should look at that, but I'm pretty sure it is.
Yeah, it's pretty much
You'd expect transitional crust to be rougher. I mean, I'd expect to see some structure in it.
Yeah, it's there's all those paradoxes in the basin, as you know, as we know. Okay.
That's like you and I, a paradox.
That's a paradox.
Any other questions?
Do you have follow-up cruises in mind? Still trying to get them to drill it?
Oh, tempt me with my dreams, will you? I'm probably going to retire in 2 years. And the timeline to get an NSF proposal funded is longer than 2 years. So mostly I'm shopping around to ride on other people's cruises.
Hey, Bernie, just in that context, the Canadian federal budget last week announced new funding for an Arctic program to continue our Law of the Sea work. So, yeah, keep your ear to the ground.
Okay, thank you. That's an awkward posture, but I'll do it.
Keep your ear to the ice then.
Do you know where you're going to go?
Well, obviously the target is in response to the Russian revision is to go further towards the Siberian side, but there's so many open questions still, especially on the Canadian side, as you said, where the multi-year ice still resides. So there's got to be some work there for sure.
Oh yeah, no. You put a ship in a place, you'll find something to do.
Yeah.
I just heard from the Chinese guy today, Tao Zhang, that they're going back to Gackle Ridge.
Yeah, no surprise.
Yeah. Yo.
When you're planning your lines, what are you using with my lines? Are you using bathymetry? Is that?
Well, you try to look at everything. What are you going to, like, for example, the bathymetry would tell me nothing about the position of that mid-ocean ridge.
That hurts me a little.
Well, but it's just, it's dead flat. So the gravity was what I used there. For the Chukchi borderland itself, it was mostly the bathymetry. That signal told me everything I needed to know about where I wanted to see what structure. Okay.
I feel like I can't be the only person in the room who just learned that air guns exist. And I followed it shoots air and goes, how does it, it's for mapping stratification, correct?
Yeah.
How does it do that?
No. But what you put in the water is this pressure wave, it's sound. And typically, the frequency of an air gun shot is between 1 and 100 hertz. And that at that low frequency, that signal will penetrate the sediments quite some distance.
And is it a frequency lower than we're able to create with sonars?
Beg your pardon?
Is it a frequency lower than we're able to create with sonars?
It's hard to make a transducer to make that kind of noise.
Really hard.
Yeah, really hard, which is why the oil industry tows air guns.
They're not air guns, Bernie. They're pneumatic sounding devices.
Oh, is that what they are, Dave?
Yeah. You can't use gun. You can't use the word gun if you want environmental approval. Come on.
Every time I talk with you, I learn something.
David, we're New Hampshire.
Oh yeah.
Where are you at, Dave?
Yeah, guns aren't allowed here. Sorry. We're a 2 beer limit, no guns.
So across the,
Pneumatic imaging device, is that what you said?
I call them a pneumatic sounding device. Yeah.
Okay. Thank you, I feel better now.
Yeah.
you've been politically corrected.
Well, they used to be marine mammal observers, now they're protected species observers, which is much better.
Yeah, crabs are a species too.
Yeah, we're not protected, are we? So, any other questions? Snarky remarks? Outraged diatribes? Mendacious monologues?
How about a suggestion?
Yes.
I think in this audience, people understand that continents are rock and oceans are water.
Yeah.
And that your early explanation might have gone over better as ocean basins are different than continents.
Okay.
We're doing constructive criticism now?
Well, David's going to comment on terminology.
Yeah.
I would like to point out that Bernie is pinch hitting for us. We did have another speaker planned for today, and he graciously stepped in to fill the slot because it was she had to cancel. So thank you very much.
Good for you.
Heck of a guy.
Yeah, hold it together in 2 weeks. Let's go.
Hey, Bernie, just to
All
your
this took 2 weeks.
Yes, sir.
Bernie, your point to about collecting multiple types of data when you're out there, and you mentioned about not you personally are not particularly interested in the multi-beam data, for example, in the basin, but it's a wealth of data, obviously, because we don't have any information in those regions, and we're discovering things like deep sea channels and
Oh, no, I don't mean to.
all the time. Yeah. No, just the value.
Kai's work, and I guess some of your work too, have been very enlightening about that.
Yeah, just to point out the value of collecting, all the information you can when you're out there.
Yeah. Well, yeah, that's the thing, you go out, you turn everything on. We collect ADCP data. Actually, the seismic reflection data I collected in 2011 from Langseth got picked up by some oceanographers in China to do seismic oceanography. And it turns out that they can directly image eddies in the water. And they got back to me with the paper they wrote. And I said, why didn't you use the ADCP data? And they said, we couldn't find it. And I got it for them. And so they had this image, kind of a haystack image in the water column of an eddy. And then they plotted the ADCP data, the acoustic Doppler current profiler. And one half of it was red and the other half was blue. So one part was coming out, the other was going back in. They nailed it. So it's kind of surprising what it's my noise, it's their signal.
Mm-hmm.
If there are no more questions, last chance, going once, going twice.